this is a finite system, so obviously the number of energy levels available for you is finite. Okay, and A minus operator from the ground state is not useful because you do not have any energy levels below the half H cross. Okay, so where did we stop? We stopped at this place where I said the energy spectrum is given by n plus half times H cross omega. Okay, and you put the various values of n, so you get the energy spectra, etc. Okay, and we also calculated what is the function, wave function corresponding to this state, n equal to 0. So psi naught of x was a constant times exponential m omega by 2h cross times x squared. Okay, so this is the ground state function, and these are the energy levels available for you. You can attain the higher energy states by operating the raising operator A plus on these functions. Okay, A plus operating on this function gives you that energy level 1, the first exact state. Again, you operate with that A1 or A plus, sorry, you will get the higher energy state A2, etc., etc. Okay, and you will not get any energy level below half H cross omega. That's the ground state energy, and that ground state energy corresponds to E naught. If you write, this will be half H cross omega. For the analysis, this is fine, absolutely fine. It simplifies our problem of differential equation, etc. The real systems are not in one dimension. The real systems are in three dimensions, right? So that means if you have the example which I always give you is the silicon surface and connected or adsorbed with a hydrogen atom. Okay, we use this for a lot of research purposes, experiments. Okay, we use silicon 100 surface and adsorb intentionally the hydrogen atom for various applications. Okay, now this is a three-dimensional system. That means this can oscillate in three perpendicular directions. So that means this analysis somehow we have to extend it to three dimensions. Okay, so we will extend this analysis of the functions and the energy spectra to three dimensions. Okay, extension to three dimensions. So the starting point is again to check what is the potential energy of this three-dimensional object. Okay, or the harmonic oscillator assumed to be in three dimensions. Okay, so what is the potential energy? So it will be V x y z. That means you can actually write like this, or I can take a reference of x, y, and z, and I can consider this as this particular hydrogen atom connected to a spring or connected to this coordinate system with a spring and then connected like this. So now this is in three dimensions. Okay, so it will have an x coordinate, something like this, and y coordinate, and also the z coordinate. So this will be my x coordinate, this will be y coordinate, and this will be the z coordinate. So obviously the oscillations what you have in three dimension can be resolved into x, y, and z coordinate system. Okay, so in general the three-dimensional potential can be written as the component of the potential along x-axis. Okay, so this will be, I will in general write this as kx, that is the spring constant or the component of the spring constant along x-axis. Okay, and then of course the amplitude squared plus half ky x, y squared plus half kz z squared. Okay, this is my general potential well, or the harmonic potential well in three dimensions, assuming the oscillations are very, very small. Half kx squared extended to three dimensions. Okay, now what? So if this is my potential well or harmonic potential, then I can substitute this in the Schrodinger equation and get the dynamics of the system. Okay, you can actually resolve the total Hamiltonian of the system, three-dimensional system, as having components of x. So I'll just write this cap here. So hy cap plus hz cap. Remember, the hx, that suffix xyz, corresponds to the component of the Hamiltonian along xyz, because you can resolve the potential energy in terms of xyz components. Similarly, the kinetic energy component also can be resolved into three perpendicular components. That means your kinetic energy operator can also be along three perpendicular directions, can be resolved. Okay, so just write down this one, for example, and then you can add up this to get the total Hamiltonian. So how about this one? Hamiltonian of this system along x. It will also have a kinetic energy operator along x-axis and the potential energy along the x-axis. Okay, so I can write this as minus h bar square 2m L square by del x square plus this term half k x square. This is my part of the Hamiltonian along x-axis, because it consists of the kinetic energy operator along x-axis, or the component along x-axis, and the component of the potential energy along x-axis. Similarly, you can write the corresponding value of this Hamiltonian along y and z direction and then sum it up. Okay, it's very nice that we can resolve these things into three different components, independent components. Okay, so then hy is minus h bar square divided by 2m Ly square plus half ky y square. Okay, and along the z-axis it will be hz cap. That's a part of the Hamiltonian along z-axis. Is again the kinetic energy operator h bar square divided by 2m L square by Lz square plus half kz z square. Okay, so it is just extending your one-dimensional explanation into three-dimensional by considering these as independent potential energy contributions or components of potential energy along xyz. Correspondingly, you will have these components of kinetic energy in terms of operators along xyz. So what do you get as a complete eigenvalue equation? You have the potential energy, you have the kinetic energy operator. Now you just substitute in that eigenvalue equation. Okay, so your total Hamiltonian will be the sum of all these terms. Okay, so this will be minus h bar square divided by 2m L square Lx square plus this term, the half kx square, plus again along y and z direction. Okay, plus z direction. So this is along y and this is along z direction. Okay, because this is the total Hamiltonian. H is in terms of hx, xy, and hz. So I just put this and add these two terms. So this you have to solve. If at all you are considering the three-dimensional case, you have to solve this equation. That means you have to use this Hamiltonian operator, operate on the function, three-dimensional function, and you will get the energy values in three dimensions. Okay, that's my eigenvalue equation. H operating on the function Now this function is x, y, and z, right? This will have a three-dimensional property. So I will get this energy in three dimension, and again this x, right? This as x, y, and z. Okay. So that's a very, very easy task. Okay. But let's not go into the derivation part, but I will explain you what actually really happens if you apply something like this. Okay. Now, we'll consider each of them independently. Okay. So, if you write the equation like this, that means you will write a combined equation operating on psi. Is it not? The combined equation operating on psi will give you this energy in three dimension, and again this function. So this term operated on this function, this term again operating on this function, and the z component again operating on the function. So you can independently operate this term, the Hamiltonian, on this function psi. So now you know how to do this. So we will operate hx on psi, and we will see what really happens, and that can be extended to y and z direction. Okay. So any hint? This is a harmonic oscillator. So the potential energy is given by kx square, and the harmonic oscillator in one dimension gives you discrete values of energy, n plus half times h cross omega. So that means if you operate this x component of the Hamiltonian on psi, you should get a term which gives you energy along x-axis. Similarly, if you operate this hy on this function, whatever function it is, on the function, then you will get this ey. Okay. Similarly, along z-axis, what is ex? Ex will be some number which is along x-axis plus half times h cross omega. And now this omega is also having x component because we considered a general case of kx, ky, and kz. That means your omega x will be square root of kx divided by m. Omega y will be square root of ky divided by m. Omega z will be kz divided by m. This is my general harmonic oscillator. If you have a half kx square, v of x is half kx square, then k is given by, or the frequency of oscillation is given by k by m, square root is the frequency. So if you can resolve this potential energy in three components, we intentionally consider an anisotropic potential, okay, harmonic potential. So that means this will also have omega x, this will also have omega y, omega z, and these are given by this direction, these equations. So that means if you operate this on the wave function, you will get these energies En equal to n plus half times h cross omega x. Okay. Along y, for example, it will be n plus half h cross omega y. Along z, it will be n plus half h cross omega z. Okay. And then, of course, you can combine it because my total equation is something like this: h, which is the combination of x component, y component, and z component. So now, for simplicity, I'm telling we will independently operate that on the wave function. And now I know what I get. Just for simplicity, I'll write this as n suffix x, for example, if you use the x component, and h cross omega x, ny plus half h cross omega y, nz plus half h cross omega z. Okay? Yes. So, if at all, if you use this equation, psi of x comma y comma z, this is my idea. So you will get this energy value times x, y, and z. That's my standard eigenvalue equation. And now I know, since this being a harmonic oscillator, these energy values should have this form. Okay? So this will be n plus half or h cross omega x n plus half times this function x, y, and z. Okay. Now I can write this x, y, z because I'm just using the x component, so y, z component will not contribute. Okay. So this is along the x-axis. Similarly, you can use this for y-axis and z-axis and substitute in this parent equation. So this is along y plus you have this z term. Okay. Are we in the same page? Yes or no? Okay. So what you get will ultimately is this E in 3 dimension x, y, z is sum of all these energies, sum of all these terms. Okay. So I'll just erase this. And this will be h cross omega x times nx plus half. This is along x-axis plus h cross omega y ny plus half plus h cross omega z nz plus half. This is the general energy level or energy eigenvalue you will find when you have this Hamiltonian operating on this general 3-dimensional function. Okay. When I have 1-dimensional function, what did we get? We got n plus half h cross omega. There was no reason why you had to consider omega x, omega y, or omega z, because the consideration is 1-dimensional problem. But since you can resolve this Hamiltonians into 3 independent parts, you can actually resolve the energies also in terms of individual components along x, y, and z. Okay? So this is my general equation for the energy. And you can also call this x direction, y direction, and z direction as the direction of quantization. Because n, x, ny, and nz are discrete values. Remember, n is 0, 1, 2, 3, etc. So obviously x, y, z components also are discrete values. So you can call x, y, and z are the directions of quantization. And nx, ny, and nz, you can call it as certain quantum numbers. Okay, so nx, ny, and nz are quantum numbers, and individually these can have 0, 1, 2, etc. Okay. How about this function then? So you know the energy now. So that means you should also extend the 1-dimensional function into 3 dimensions. Okay. Yes. We will reduce this to a spherically symmetric. Then you will know what I mean having written x, y, z component. Yes. You will come back to the same question after we resolve this to spherically symmetric problem. Okay. This is not a spherically symmetric problem. I'm just considering different values of k, x, ky, and kz. Once we reduce that to a spherically symmetric problem, then you will understand why I can write this as sum of the x components. Okay. Yes, yes.
It won't be a function.
Oh, okay. So you want me to delete this? Uh, no, but you have to write x, y, z because these n's depend on x, y, z. Your values of the total energy now is a function of the frequency along x-axis plus also the quantum number what you choose along x-axis plus omega y and ny, omega z and nh. So in that sense, you can write this as x, y, z or the function of three directions. While if this potential half k x square I said is spherically symmetric, then this reduces into some other form. Okay, we'll check that later. First, let's try to find out what is the function in three dimensions. And this was the ground state of the harmonic oscillator along one dimension, whether it's along x-axis or y-axis or z-axis, you can write in the same form. Okay, the resultant wave function x, y, and z along three directions are written as psi along x or this psi y, oops, y and psi z. Okay, the resultant function is written as the product of the individual functions psi x, psi y, and psi z. So that means you can consider the product of x, y, and z. While you also have to consider these constants, remember, prefactors. So when you write psi x, for example, then this will be ax, and then the other one will be ay, and the other will be az. Okay? Let's try to reduce now to the problem of spherically symmetric potentials. Okay? So if at all, if you have a spherically symmetric potential, that means the potential energy do not depend on the direction. It just depends on which point you are considering along the three dimension. Like this x dependence or y dependence or z dependence will not consider now because you are considering a spherically symmetric system. Okay? It just depends on what value of x you are considering, and that value of the potential is same throughout the or x, y, z direction. Okay, so now what you can do is you can reduce the energy eigenvalues and the functions to spherically symmetric case. This already tells me that the spring constants x along y and along z are same. Okay, and I will consider this as k because it's non-zero value, and this equating kx and ky and kz equal to some number corresponds to, this also gives you that omega x or frequency along x, frequency along y, and frequency along z are same. Kx square, ky square, and the kz square. If you consider the spherically symmetric case of the harmonic oscillator, so now this is same along three directions. It is not depending on any direction. Okay, it just depends on at what distance it is there with respect to your origin. If you substitute these values, your potential reduces to some simpler form. Okay, you just write down the potential Vx, y, z we wrote equal to half kx x squared plus etc etc. Okay, so what is the potential now? If you consider the spherically symmetric potential, so x, y, and z, I'll still write x, y, z as half kx x squared plus half ky y squared plus half kz z squared. And I said in all the direction it is equal, the spring constant equal, the frequencies are equal, so I can write this as half k ky, kx, and kz are equal. So I can just substitute k, and this will be x square plus y square plus z square. This gives you half k. I can write this as, let's say this is x, this is y, and this is z. Now I can write this as r in three dimensions. So that means what you have here is half k uh, r squared, correct? Yes. If you have half k r squared, then what is the force on this? It is again the same, the partial derivative with respect to r. Okay, so the force will be minus this v divided by r, so it will be minus half k to r. This is minus kr. But you can substitute k in terms of the frequencies. It is omega. Okay, so this will be minus m omega square r. Okay, this is my force. So this force is in the opposite direction. So obviously the force is somewhere here. So I can write this as Fr. Okay. So it is just like in the x direction, for example, you find the first order differential with respect to x. Similarly, you can find the first order differential with respect to r. This is in a three dimension. Now, how about energies now? En is n plus half times h cross omega. Now these omegas are same, omega x, omega y, and omega z are same. Okay. The only non-equivalent term in these are n's. Okay. So I can write the total energies in three dimension as so. What is the total energy or any eigenvalue, for example? E is h cross omega nx plus half plus h cross omega ny plus half plus h cross omega nz plus half. I'm writing intentionally this nx, ny, and nz different intentionally. Okay, so what do you get? This is just the reduction of my earlier equation where you had different values of omega x, omega y, and omega z. Okay, so this becomes h cross omega. It's a common factor. So this will be nx plus ny plus nz. I can club these together, and you have half, half, half is 3 by 2. Wow, wonderful. Half plus half is half plus half plus half is 3 by 2. Great. We should study this in MSc. Okay, these are quantum numbers, I said. Okay, nx, ny, and nz are quantum numbers. It takes values of 0, 1, 2, 3, etc. So the sum of these nx, ny, and nz are also numbers. Okay, so instead of writing like this, I can write h cross omega is some value of n plus 3 by 2. So this is my energy spectrum. Okay, this is my energy spectrum in three dimension, where n is h cross omega times n plus 3 by 2, where n is nx plus ny plus nz. As I said, nx, ny, and nz can independently take values 0, 1, 2, 3. Okay. So if this is the energy spectrum, then you should tell me what is the ground state energy. 3 by 2 h cross omega for what value of n, x, ny, and nz? So 0, 0, 0. So that means if you have 0, 0, 0, that will give you the ground state. Okay. So let's see. I'll just plot this now with respect to energies. Okay. So while plotting, what I do is I just write this as En divided by h cross omega. So if you divide this En divided by h cross omega, so it will be n plus 3 by 2, where n is 0, 1, 2, etc. etc. So n plus 3 by 2 is, for n equal to 0, it will be 3 by 2, n equal to 1, it will be 5 by 2, etc. Okay. So this will be 3 by 2, and this will be 5 by 2, this will be 7 by 2, and this will be 9 by 2. Let's see what happens. So this along y-axis you will have En divided by h cross omega. Okay. So for n equal to 0, 0, 0, you will have one energy level here. You will also have energy level here. So you will have energy level. You will have energy level. So this means these are energy levels. Okay. So I'll write correspondingly all these nx, ny, and nz numbers. Okay. So I can write here as quantum numbers. Nx, ny, and nz. Okay. So as you know, for 0, 0, 0, you'll get one energy level. That is 3 by 2 h cross omega. That's what it is. Okay. So then what is the excited state? 1, 0, 0, 0, 1, 0, and 0, 0, 1. It becomes same. Okay. It will be capital N will be 1, so it will become 5 by 2 h cross omega. So this will be here. So that means you will have three values of this nx, ny, nz combination. Okay. So that means I'll write this as 1, 0, 0, 0, 1, 0, and 0, 0, 1. For all these combination, all the three combination, energy is same, remember. Okay. So what is the difference? The difference is the kind of wave functions you have for this state and this state and this state. The wave functions are different, but they define you the same energy. So that means I call this as degenerate state. So the degenerate energy level is an energy level which has the same value of energy for various values of the functions. Okay. So here it can have three combinations of numbers nx, ny, and z. So I can call it as threefold degenerate. Threefold degenerate. Okay. So if you want, you can write here the degeneracy. Okay. So here there are no degeneracies. It's only one ground state, and it is defined with one single function. So I can call it as maybe 0. Okay. Or 1. 1. Let's call it as 1. So this has 3. How about this energy level? Okay. So it will have how many? 1, 1, 0, and 1, 0, 1, 0, 1, 1. That's all. 2, 0, 0, 0, 2, 0, and 0, 0, 2. Okay, I'll write it here. Okay, so this will be 2, 0, 0, and 0, 2, 0, and this will be 0, 0, 2. So it will have uh, six-fold degenerate. That means all these functions given by nx, ny, and nz Okay, Nx, Ny, and Ng have the same energy, so that means I can call it a six-fold D. Okay, and the next one, I think has quite a number of degeneracies. Uh, I think it has 10. So this will be 10-fold degenerate. Okay? Just find out the numbers. I have these numbers written here. So this will be 111 and 120, and the combination of these things 102 and 210 and 201, 012, 021, 300 and 030 and 00. Okay, so it will have 10-fold degeneracy. 111 gives you 3. It is 6 by 2 plus 3 by 2 is 9. Okay, so it will have 1, 2, 3, 4. Yes, 4 plus 3 plus 3 is 10. Yeah. Yes. And in general, you can write the degeneracy as n plus 1 multiplied by n plus 2 divided by 2. Okay, is that correct? Yes. For n equal to 0, 1, 2, etc. etc. So this already tells you that if you consider the spherically symmetric system, it directly gives you degeneracies. Okay? And I told a few weeks back somebody that please tell me about degeneracies and in the particle in infinite box. Okay? Extend the ideas of particle in a box, one dimension. Somebody's okay. Extend the idea of particle in a box in one dimension to three dimension. Okay, and you will get the similar degeneracies because you will again have the same similar quantum numbers nx, ny, and nz, where your energy values were defined by En was n square pi square h bar square divided by 2m a square. I think I also gave you an assignment about these things, right? And for extension to three dimension, you just consider A equal to B equal to C and find out what happens if you do not have B, A not equal to B, not equal to C. Those degeneracies are lifted. As soon as you have the system going beyond the symmetry, you will have the degeneracies lifted. Okay? So that means this case is an ideal case. The spherically symmetric system is an ideal case, okay, where you have these k's, that means k, the spring constant same along three perpendicular directions, and correspondingly the frequencies are same along three perpendicular directions. That's idealized system. But you do not have an idealized system always. Okay? So there will be some preferred directions. So obviously the functions are different, and the energies will also be different, even though you go to the higher energy states. Okay? Yes, please. Yes, we will go to this degenerate orbitals now in 2 minutes. Okay. So the next step is to actually find out what are the functions defining here. Okay. If you can define the ground state function for this three-dimensional spherically symmetric oscillator, then you can apply the same rule of using this A plus to go to the higher energy states. You can use the same rule of A plus again to this energy level. You go to the 7 by 2 energy level, and so on and so forth. So let's try to find out what is the ground state first of all. Okay, then you can apply that for the using this operator. That will be your digital assignment 2. Okay. You use this function psi naught x along 3 perpendicular directions. Now remember, this is spherically symmetric system. That means x, y, z components are same. Okay. So let's try to find out that. And the procedure is almost same. You just find the product of the individual functions along x, y, z directions. Okay. So let's do this. So you have the function along x as a constant times exponential minus m omega divided by 2h cross times x squared. Right. This is my function along x-axis. That's a one-dimensional oscillator we consider. Okay. So you can extend this to the y-axis as psi naught y as I will write this suffix ay times e power minus m omega divided by 2h cross times y square. Okay. Similarly, along z you will have az times e power minus m omega divided by 2h cross g square. Okay. So we derived this equation along x-axis. So the ground state function along x-axis, one-dimension oscillator, is in that form. So now I consider the ground state function of the oscillator along y-axis, oscillator along z-axis. Okay. Then you find the resultant function along x, y, z by finding out the product of these three, x, psi naught y, and psi naught z. Once you find this product, then you use this operation of raising operator, for example. You go to the next energy level here, the first excited state. Okay, let's try to find out this one. So I'll just write a x times e power minus m omega 2h cross times x squared times a y e power minus m omega divided by 2h cross y square times az e power minus m omega 2h cross. If I miss some terms, please stop me. Z square. Okay. So what is this? Ax, ay, az e power exponential minus m omega 2h cross x square plus y square plus z square. I consider here omega same because I'm still considering a spherically symmetric system in 3 dimensions. So that means omega x is omega y is omega z. Okay. So this x square plus y square and z square, according to our coordinates, I considered it as r. Okay. So this is along in 3 dimensions. So I consider this as r. So it will be r square. So it will be ax, ay, and az times exponential minus m omega 2h cross r square. Okay. This is my ground state function along x or in 3 dimensions, psi naught. You can, in fact, since this is a spherically symmetric system, omega, you can write ax and ay and az in this using these units. Okay. So this will be, in fact, what was a here? I think a we wrote it as m omega divided by pi h cross power 1 power 4, right? I wrote this A, the prefactor, as m omega pi h cross 1 power 4, 1/4 of the power. So you can just substitute here. Okay? Now this omega is same because I'm considering spherically symmetric system. So in every term you will have the same m omega pi h cross 1 power 4. So it becomes 3 power 4, 3 divided by 4. Okay? So I'll just keep it like this now. Okay? Times e power, or let me substitute. So this will be m omega divided by pi h cross 3 by 4 times e power minus m omega divided by 2h cross times r square. Now what do you do? To get the equation or the wave function at the second level, so we have this, uh, what is this? E divided by h cross omega, so it's 0, so this p by 2, right? This is 5 by 2, this is 7 by 2. Remember, this R has the components x, y, and z. The R, the ground state function, has the contribution from x, y, and z, the quantum numbers x, y, and z. So obviously, when you go to the higher state, that is 0, 0, 0, and 1, 0, 0, you will have the contribution from x, you will have the contribution from y, and you will have the contribution from z. These are quite independent functions, and that contribution 1, which is non-zero, comes here. Okay, r square is x square, y square, and z square. So the x component only comes into picture for this 1, 0, 0 state function. 0, 1, 0, you have only y component non-zero, so that means this will have only y component. This will have only the z component here. So that is why you have those multiple functions corresponding to the same energy level. Similarly, for the higher energy state, for example, depending on what x, y, z corresponds to, you will substitute that here. Provided you first operate this A plus on this ground state function. You understand? We have the ground state here, psi naught. So to get the function in the first excited state, we use the raising operator. So what was A plus? A plus was minus IP plus m omega x. And these two are the operators, remember. So I use this operator, A plus, on this function psi naught x, y, and z. I will get E naught plus h cross omega psi naught x, y, and z. And this one is the first excited state. Okay? Operation of this A plus operator on the ground state function will give you jump to the first excited state. And now you just use this P is first derivative with respect to x, and the x operator. X operator is just multiplication by x. So that means the first excited state will have a term which has x here. Along 1, 0, 0, for example, it will have x. Along this y 0, 1, 0, it will have y. Along 0, 0, 1, it will have z. Z times the exponential form. Okay? So your homework or the assignment will be to find out the first excited states corresponding to 1, 0, 0, 0, 1, 0, and 0, 0, 1. Let me write down the statement. Okay? So find the wave functions